Good day, Year 12. This is Lesson 2 of Differential Equations. So we've got our Lesson 2 notes here. Our aim here is to learn how to solve differential equations of this form. The importance of this form is that dy dx is a function of y, not a function of x. So in the last lesson, we had things like dy dx equals 4x squared. That's easy, just take the primitive. Why is it easy? Because when we take the primitive, we're integrating. And when we're integrating with respect to a variable. And the only thing we can do here is integrate with respect to dx. And so basically we get y equals the integral of 4x squared dx. It's like that moves up there and we pop in an integral. And so it's kind of like multiplying by dx, but in order to allow that multiplication, you are taking an integral. I'm sure more could be said about that, but I'll stop there. Anyway, the key thing is here that the variable in the expression and the variable that we're integrating, they match, and that's important. Okay, so what about if you've got dy dx equals 4y squared. Then if you wanted to do a straightforward integration, you've now got y equals the integral of 4y squared dx. And we've got a mismatch here. And so that doesn't work. So a different technique is needed. It's actually just a little bit of a twist. Okay, it's this skill that you're learning today is not very hard. It's really one little thing and then you're back to normal integration. I'm sure there'll be some subtleties as well. Okay, so just tidy all that up and get on with it. So yeah, it's a lot. There's only one concept today, not like the last lesson. All right, and the exercise is just to apply that skill. All right, I'm not going to say how to do it yet. I'm going to demonstrate how to do it. Y dash is 1 over 2y. Well, the first thing we need to do is write it as dy dx equals 1 over 2y. I deliberately wrote it like that so that we could make a big deal about how we need to write it in this form. Okay, dy dx equals 1 over 2y. And then the awesome thing we can do is turn them upside down. Dx dy equals 2y over 1, or just 2y. We're taking the reciprocal. Can you do that? Yes, you can. Can I justify that? Maybe, later. So we've got dx dy equals 2y. Basically, these are equivalent statements about the rate of change of a function. It's just that one of them is expressed in where x is the independent variable, and the other one is where y is the independent variable, and we're looking at how x changes with respect to y. All right, and you could look at that on a graph and something. Okay, so if we have dx dy equals 2y, then we can do this. X equals the integral of 2y dy, and we're away. That's an easy integral. X equals half y squared plus c. We're taking a primitive, so in goes the plus c. And now we do need to write this in terms of y. So we can have, why have I got a half there? My apologies. There we go. The primitive of 2y is y squared, not half y squared. We need to write this in terms of y, so we'll get y squared equals x minus c. Now we don't have any initial value or anything that we can use to find c, so we just have to keep it with us. And now y equals plus or minus the square root of x minus c. Okay, so this is not a function, this is a relation. It looks like if c was 0, then it's a sideways parabola. And if c was not 0, like if c was 5, then it would look like that. All right, so the C, the plus C here, means that our family of functions is not being shifted up and down, it's actually being shifted left and right. Okay, the next question. And if we had a value that we needed to solve to find C, we'll see later, then we might choose between the plus and the minus, but for now, this is a good general solution, and that's what we're after. Okay, question B, another general solution. So dy dx equals 8y, taking the reciprocal, dx dy equals 1 over 8y. And x equals integral 1 on 8y dy. And so, well, just going to take that out the front. I would have just taken that out the front straight away, but whatever. And we get x equals 1/8 ln absolute value of y plus c. Okay, we don't have any way of finding c, so we proceed. We want to make y the subject. So let's get rid of the 1 on 8. So 8x equals ln absolute value of y plus 8c. I would happily write just c here. C is a constant. We don't know what the constant is. If you multiply it by 8, it's still a constant, and it really doesn't matter. But that might confuse some people, so I'm just going to pretend that C is like an actual fixed quantity here, and I'm going to multiply it by 8. Either way, doesn't matter. Okay, so we're still continuing to make y the subject. So ln absolute value of y equals 8x minus 8c. And absolute value of y equals e to the power of 8x minus 8c. All right, are we going to do any better than this? Yep, we are. I'll just make some room for myself. Okay, so bit of index laws. E to the 8x times e to the negative 8c. And then we can do a cool thing here where we go absolute value of y equals capital A e to the 8x, where capital A equals e to the negative 8c. Right, we've just taken a constant, c, or e to the negative 8c as a constant, given that a different name, a, and that tidies this up nicely. All right, and so if absolute value of y equals that, then we've got y equals plus or minus a e to the 8x. And got a couple of things to say about this. I'm just going to finish it first. The important thing is that the a, we don't know if that's positive or negative, or do we? All right, I'd better say it now then. If you look at what a is strictly positive. Okay, e to the something is always positive. Always positive. So what we have here is a positive quantity, and we've got absolute value as a positive quantity, and so y equals plus or minus a e to the ax. But we can relax that a bit, not relax it so much, but we can just say y equals a e to the 8x, right, where a can be positive or negative. All right, and we await further information. Right, if we were told some values, then we could find the value of a. Right, let's have a look at a couple of things on this page. We've looked at this. early on here we had dy dx equals 8y, so dx dy equals 1 on 8y. All right, now over here, all right, so I suppose y can't be 0 if it's on the bottom of a fraction like that. Well, we're going to see about that. What about here? Oops. What about, excuse me, what about here? Y not equal 0? It's on the bottom of a fraction. Now, you might remember last lesson we talked about trivial solution or a constant solution. So this one has a constant solution of y equals 0. Okay, for the same reason, it's just like we did last lesson. Okay, you've put y equals 0 in here, then the left-hand side will equal the right-hand side. So it's a solution. So we've got y is not equal to 0 here, but y equals 0 is a constant solution. Can I just say that if you're just asked to solve this, then an answer like that or like that is going to be fine. But if the question had a bit more information or directed you to consider a constant solution or something like that, then that's what I'm telling you about now. Okay, over here, well, actually, so what does y equals ae to the 8x look like? Well, it looks like that, or if a was negative, it looks like that. And depending on the value of a, well, you know, see how none of these are 0? And so in between these positive ones and these negative ones, there's this 0 constant solution. All right, so yeah, if you're solving this, if you want to give a complete solution of this, then basically y equals ae to the 8x, and a can be positive, negative, or 0. And over here, we looked at, all right, so if y dash equals 1 on 2y and y does not equal 0, well, what did our graphs end up looking like? Well, I just drew 2 of them. All right, they're sideways parabolas, or they're plus and minus square root curves, and y cannot equal 0 apparently. Well, these are these are the places where y equals 0, and what's the gradient there? Well, the gradient there is, well, it's vertical, and that means that the y dash literally is undefined at these points. So wherever you draw the resulting graph where y equals 0, then y dash is undefined. Right, so it all fits together. All right, so that's a side one. We've talked about domain restriction. We've talked about trivial solution. And yeah. All right, next page. Question 2. You could treat this as a your turn, like you should be able to pause the video and solve this. So, you know, I've got the information here, plus we know that there's a particular point. So it's not going to be, you know, there might be some subtlety to do with that, but anyway, if you want to pause, go for it. So we've got dy dx equals 5y squared. So that means dx dy equals 1 on 5y squared. And so x equals the 1/5 integral y to the negative 2 dy. And we can get that. That's 1/5 stays for the ride. That's y to the negative 1 over negative 1 plus c. All right, so x equals, that's 1 on 5y plus c. Now, we could rearrange this and make y the subject, or we can find c now. I'm going to find c now to demonstrate that we can. It works out that it's probably the best thing to do in this case. The numbers work out nicely. So sub 0 comma 1/5, and we get 0 equals 1 over 5 lots of 1/5 plus c. Just be careful of the order. We've got x there and y there. That's 0 equals 1 over 1 plus c, and so c equals -1. And so we have x equals, going back here, oops, my apologies. I've made quite the mistake here, so let me change to red. There was a -1 here, so that's negative, that's negative, that's negative, and that's positive. Okay, order is restored. X equals -1 on 5y plus 1. And now let's get y as the subject. So x minus 1 equals -1 on 5y. So 1 on 5y is 1 minus x, and y equals 1 over, jumping ahead, 5y, reciprocal of both sides, 1 on 1 minus x, and y equals 1 on 5 lots of 1 minus x. All right. So a graph of that has a vertical asymptote at 1/5. It's an upside down hyperbola, and so it looks like this. Right, it goes through the point 0 1/5 as required. And just a important point where we have y dash equals 5y squared. What do we know about the expression 5y squared? First of all, it's always positive, isn't it? It's always positive, or 0. But y can never be 0 here, which means y dash can never be 0. Y can never be 0 in this graph. And I suppose, once again, we have a trivial solution, y equals 0. So if we look at the like some small values of y, whether positive or negative, okay, some small values of y, 5y squared is also a small value, and that means that y dash is a small value. It's nearly flat, okay. And if we look at some large values of y, whether positive or negative, then 5y squared is also a large value, and so the gradient is a large positive value, and it's very steep there. So with differential equations, when we look at a graph, we're looking much more at what the gradient of every part of the graph is and not what the y values are. It's a change of thinking. Okay, I'm going to show this in GeoGebra, not going to take long. I've got a point A here that I can move around, and I've got a slope field for this particular equation, 5y squared. And if I plot the solution to this differential equation, then once again, I hope you can see the way in which it follows the slope field. Just following the gradient around. Okay, and as I move it around, if I put it on 0, 0.2, then we get the graph I showed you before. Okay, I'm a little bit, I'll just correct that. 0, 0.2. All right, so there we go. That's the graph, all right? And the equation's given to us on the left-hand side there too. -1 over 5x minus 5. All right, and if I move a around again, then the equation changes a lot, doesn't really change its form. If you put a on the x-axis, interestingly, it says that the solution is undefined. I think that's a limitation of the software more than anything else. Okay, back to this. All right. Okay, for question B, this will be straightforward enough, but there's a little kick to it. So I'll give myself plenty of room here. So for question B, f dash x equals that. Well, of course, we're going to write it as dy dx, not talk about f of x anymore. And that is 1 on 2y minus 4. And so taking the reciprocal, dx dy is 2y minus 4, and x is the integral of 2y minus 4 dy, which gives us y squared minus 4y plus c, looking like a perfect square almost, isn't it? We will be completing the square in a minute. The information we're given, f of 4 equals 1, I'm going to write that as x equals 4, comma, y equals 1. And sub that in. So 4 equals 1 squared minus 4, lots of 1 plus c. That's negative 3 plus c, so c equals 7. And so we have x equals y squared minus 4y plus 7. All right, so that's like a... let's imagine this was worth 3 marks. Well, we've probably got 2 marks so far, maybe. Okay, let's make y the subject. It's just algebra now, not calculus. So we'll get x equals y squared minus 4y plus 4 plus 3. So completing the square, x equals y minus 2 squared plus 3. Get y minus 2 squared equals x minus 3. Y minus 2 equals plus or minus square root x minus 3. And so y equals 2 plus or minus the square root of x minus 3. Okay, what does that look like? Here's your y equals 2, here's your x equals 3. It looks like that. Now, f of 4 equals 1. So here's 4. I think that's right, but anyway, f of 4 equals 1. No, it's not right. Sorry, that was very... That's actually 7, where that goes through. So f of 4 equals 1 means that we take the negative part. Right? So if we look at this, according to the textbook where this comes from, we need the negative, right, to minus square root x minus 3 because of the point 4 comma 1. Now I looked at a graph here, but you can substitute in, right? You've got 1 equals 2 plus or minus square root of 4 minus 3. Okay, so that's the true statement, 2 minus. All right, now, all right, so we have y equals 2 minus square root x minus 3. Now, I've got 2 things to say about this. First of all, in general, I think that's the better answer. When we're dealing with differential equations, there's no guarantee that our answer is going to be a function as opposed to a relation. We should not be prejudiced against functions. Later on, we'll do a differential equation where our answer is a circle. And if we're told that, oh, this point is on it, then it doesn't mean we have to do just the top half of the circle, because guess what? That point is on the whole circle as well. So I'm a little bit uncomfortable with getting to this point and then feeling like we need to choose between the plus and the minus. All right, that's my first point. My second point is I'm willing to make an exception here because of the way the question was phrased. See how it didn't say, right, what it could have said was y dash equals 2y minus 4 negative 1. All right, it expressed it in terms of f dash x. Well, I guess f is a function, isn't it? And so if f is a function, then we should be answering in terms of f of x, shouldn't we? And so that is the reason why I will allow for this restriction to take place. So yeah, just be mindful of context. There's nothing wrong with relations. They're perfectly good, especially in the context of differential equations. But functions, well, this as it stands, you can't really write f of x equals 2 plus or minus square root of x minus 3, because that's giving two f of x values for every one x value, and that's not good. Okay, just try to be quick now. Why is it that this works? So this is the heart of today's lesson, that dy dx times dx dy equals 1, meaning that we can have dx dy equals 1 over dy dx. Why does that work? Well, it's because dx and dy are small pieces of x and y, but they're infinitesimally small. Now, we always tell you that you cannot treat dx dy or dy dx like a fraction. They might behave like a fraction in a lot of ways, but you have to treat them as a concept that's not really a fraction. But they do come from a fraction. They come from this. So delta x and delta y, if those really do mean small but finite pieces of x and y. And so if they're actual real numbers, then this statement is true. And dx over dy, not that you pronounce it like that, just dx dy, that is the limit as y approaches 0 of delta x over delta y, which is the limit of, as y approaches 0, of 1 over delta y over delta x. Now, I'm going to put a question mark here and say that's 1 over dy dx. Like, I'm putting a question mark because I don't know. I mean, obviously it's true. We're told that it's true. We have to use it. From here to here looks pretty true to me, but maybe there's some subtlety that needs to be proven. Anyway, I just want to give some justification, even if it's not 100% complete justification. I wanted to give some justification for why we can do this. Okay, quick comment. This is inspired by the Cambridge text. It didn't occur to me myself. If you have, so the differential equation that we're solving here is independent of the independent variable. That's a sort of almost a pun, isn't it? So if we have dy dx is some function of y and not x, and so basically it means we are not reliant on the independent variable, which is x, to calculate the rate of change. Okay? Basically, we're saying that the rate of change is dependent only on the value. Now that, to us, is like familiar from exponential growth. But there's a nice subtle point to be made here. This is like the laws of physics, where the independent variable is usually time. The laws of physics are independent of time, and so you tend to get differential equations in physics, like this means acceleration is negative g. That's independent of time, or the acceleration is negative k on x squared. Right? The further you get from something, the weaker the gravity or the weaker the magnetism. But it doesn't matter what the clock on the wall says. It only matters where you are with respect to the magnet. Okay, so in physics, you tend to get differential equations that are like the ones we've done today because the independent variable time plays no part in them. Okay, question 4 is here, not because it's difficult, but just because it's got more words. Right? So I'd encourage you to pause and do this one yourself first. But I just want to make sure that we cover any vocabulary that we need. All right, so consider the differential equation dy dx equals 2 minus y. So A, what is the constant solution of this equation? Well, it's y equals 2, okay, because that produces left-hand side equals 0, right-hand side equals 0 for different reasons, okay? 2 minus 2 is 0 on the right, and dy dx is 0 on the left. Right, so that's the constant solution. Right, B, use separation of variables. That's next lesson. Take reciprocals, that's better. Use take reciprocals to solve this differential equation. So dx dy equals 1 on 2 minus y. And so x equals negative, get ahead of myself, integral of 1 on 2 minus y dy. Okay, to make that a better integral, I want it to look like that. X equals negative log absolute value y minus 2 plus c. All right, and then I would continue and make y the subject, but that's what question C is. Make y the subject. Well, I get y equals 2 plus a e to the negative x. Earlier in the video, we did something that has similar working, so I'll just leave it like that. Okay, so I made y the subject, simplifying the constant part of the expression. That's where you have something like, I had a line of working plus or minus e to the c times e to the negative x equals y minus 2. So simplifying the constant part of the expression, well, that's this part. Okay, so, all right, now D, what does it say? Check that the constant solution is included in your answer to part C. Ooh, you've got me. All right. So here I was thinking this is the answer, right? And I'm done and I can move on. But we found a constant solution earlier on, which is not covered by this, right? You cannot get y equals 2 from the expression y equals 2 plus a e to the negative x, unless a was 0. Okay. All right. I take that back. Yes. Because a can be 0. Right, and question E, find the solution for the initial condition y of 0 equals 3. All right, so this is just really straightforward now. So x equals 0, y equals 3. Putting into this, we get 3 equals 2 plus a e to the negative 0. So 3 equals 2 plus a e to the negative 0 is just 1. And so a equals 1. And that gives us y equals 2 plus e to the negative x. Okay. That's the end of the video. Enjoy the exercise.